So, can you see my screen now?
Yes, sir. We are able to see it.
Okay. Thank you so much, Professor Sonawane. Thanks for the kind words. So, what I'll do, I have planned this talk in such a way that through the fact that it's an interdisciplinary participants and right from a couple of PG students to professors and I must at the outset mention that there will be plenty of participants who will be having much more knowledge than me in this particular subject and otherwise also. So a couple of general slides, if you find it, please ignore. Those are meant for the students and the research scholars who will get benefited. So I'm pretty aware and cautious that the participants are very, very knowledgeable. This is how I planned my talk. So I'd like to still prefer, although there must be some introductory lectures as far as nanotechnology and science is concerned, but I'll just brush up the things like with a few slides and we'll look into very few aspects because I remember I used to take some lectures, voluntary lectures in some colleges on science. And then a couple of things about the risk of nanomaterials, which is sometimes an ignored area because on the Environmental Institute, I developed some interest to read about it. So those couple of things we'll see. And then what is the energy scenario and nanomaterials for energy application? Not necessarily these things are from my own research because I picked up many slides from different sources. But then we'll move to the nanomaterials for water treatment and catalytic nanomaterials where I'll share some of our work for your benefits. And I'll be showing you a lot of slides. So if you have something, you can also get connected on specific aspects. So let's move. This is very briefly about NEERI. Okay, so it's a CSIR lab. It's a National Environmental Engineering Research Institute. So we are into the domain of environmental sciences and engineering, and obviously our different departments are also designed like lab, air pollution control, water technology, wastewater technologies. But recently there has been a lot of emphasis also on the materials as well as cleaner energy because we commonly say it's energy environment nexus, which is quite important nowadays. So I would request you to refer to Neeri's website if you want for the details or get in touch with me. Well, this is the reason I lead or I belong to. In fact, I have some very promising young scientists working with me. We are a group of about 5 scientists, 2 postdoc, and about 20 other students. We call them a project assistant or SRMGR. And these are the different areas we work. In fact, we are focusing on automobile emission control. And as you understand that catalysis and absorptions are two very important processes for various environmental
Sir,
applications.
sorry to disturb.
Yes, please.
Uh, your voice is having a bass, not clear.
Okay. Hello, is it better now?
This is better now. Yeah.
Fine, then I'll come closer. I think some issue with the.
Please come close to the device so that we can.
Fine, now it is better. Is it better now? Fine, thank you so much. So please interrupt me if you find any difficulty in my presentation or the voice. Okay. So these are the activities we are pursuing in our group. Okay. There's a scientist who is working on the fuel cell. I'm going to cover this. And as Professor Sonawane mentioned, we are also looking into the rural energy aspect, which is a huge environmental component. Okay, so I'm not going to touch much upon it, but just for the knowledge of those who are not familiar with these things, let me tell you, even a couple of years back, the health impact and mortality through cook stove emissions in India was more than all other air emissions put together. And what I mean is the emissions from vehicle, industry, or whatever emissions. Okay, so these are the things which were not much attended until recently when you have like LPG schemes like Ujjwala. So it is the responsibility of national lab like NEERI to look into those things. And also there have been new devices and new sources being identified for air pollution. So we take up that research in collaboration with not only different divisions, but different institutes. And then we work a little bit on the CO2 reforming, which is a part of energy environment nexus. I'll get some details. Okay. NEERI has been actively working on Clean Ganga mission, the Mami Gange. And my group is especially focusing on the sediment studies, where again nanomaterials and nanoscience plays some important role. So these are the brief. So let's understand the world of nano. I have already shown you, but you might not be able to see the nano. So that's the beauty of nano. You can't see this, and once you enlarge, okay, it becomes prominent. So please excuse me or ignore me if a couple of things have been taught earlier or explained earlier. So I'm going to be a little fast, considering the fact that there must be some talks on the general aspect. So this is the a definition why I call it, because there are plenty of definition of technology, and conventionally we say that at least one dimension, when it is within 1 to 100 nanometers, we can call it safely nanomaterials. Okay, but we should understand that it's underlined at the bottom that the exploitation of novel phenomena and properties of matter at that scale is basically the nanoscience, and its technological sort of exploitation is nanotechnology. These are the comparative scales. You must have gone through it, so I'm not going to go into the details. I'll rather skip. Okay, but we should understand that nanomaterials represents a broad spectrum. Okay, nano size in the 3 dimensions means nanopowder. Once you turn into 2 dimension, it becomes nanotubes and nanowires. Okay, in 1 dimensions. Okay, that is a sheet, which is also having a nano properties. Nowadays, we are also talking about the multi-layer coatings having each layer thickness of 10 nanometer. And what becomes interesting here, the interaction between these coatings or interaction between these nanoparticles. Okay, so there are a whole lot of science and even the related applications are still evolving, and I'm confident that it will continue for next at least 2 decades or more than that. Well, this is for comparison again that a single Rendorf contains about these many molecules. We should understand, and it's a basic chemistry, basic physics. We have been studying. It's only that of late it was realized that probably when particles become very very small, okay, there's something special. This is what I explained to you is a 1D, 2D, and 3D kind of materials. All can be categorized under the nanomaterials. Now, this is one way of understanding why nanomaterials are important, why economically they show the different properties. Okay, this curve shows the fraction of atoms exposed to the surface. Okay, what we call as a dispersion. Quite closely, we can have or we can find some analogy with the surface tension we understand or we study in fact. Or we also in chemistry quite frequently study that those molecules or atoms on the surface, they are not very satisfied because they are like the valencies are like not very satisfied because they do not have their neighboring entity, maybe molecule or atoms, okay, to satisfy their thing. So this is how the discussion goes on, okay, and you can see it makes a more or less exponential difference. This is what we call as a surface area, which is one of the very, very important parameter of nanoparticles, especially in the environmental applications, I would say. So you see, if the number of atoms are like 2 in a particle, okay, number of atoms, surface atoms will be like total number of atoms will be like 94, and half of those will be on the surface. The percent of atoms on the surface is just half. Okay, as you increase the size from 1.1 nanometer to say 5 nanometer, the percent of atoms on the surface are just 14%. Okay, and if you go for say 56 nanometer, which is very well within the nanomaterial range, the percent of atoms on the surface are just 1.5%. Okay, so this is one of the ways to explain why you get interesting properties. Okay, because you have a lot of atoms of the molecules on the surface. Okay, similarly, there will be plenty of correlations you'll find where you can correlate with the surface area as well as the temperature, the melting point, the boiling point. All can be correlated very easily. Now, this is what we understand that if you take a particle which is say fairly large, couple of inches, and you start breaking it down, okay, top-down approach, there'll be something like you will achieve 100 nanometers, okay, and after 100 nanometers, you'll suddenly realize that my material has become nanometer, okay. So, for the benefit of the students, I would like to say the actual definition or actual understanding of the nano material or nanoscience should be, you keep on hammering and you keep on reducing the size. Probably at size when you start observing different properties, that's truly the nano properties. Okay, why do materials behave differently at nano scale? So I'm sure somebody must have explained you the size quantum effect. Okay, as this picture also explained that like when we look at the materials on nanoscale, the relative importance of different laws of physics shifts and effects that we normally do not notice, such as the quantum effect, become more significant, especially size less than 20 nanometers. Okay? So typical example, this I was trying to explain to you. So you have got this picture where these materials are on the surface, their vacancies are not satisfied. While there is an atom of the molecule here, which is surrounded by the neighboring atoms and the molecules. So obviously, as we understand the electronic structure of anything, okay, determines its property, most of the property, you can expect some of the electronic properties here are changing, and therefore the properties will also change. But this gets suppressed by the bulk because your surface number of surface atoms or molecules are relatively less. When you keep on increasing this ratio by reducing the size of the material, obviously the number of atoms at the surface becomes very high and they start dominating the properties. That's how you can get change in the properties. Okay. Now, as we understand for the last 20 years, there have been a lot of push for the nanotechnology of nanoscience. What is so great about nanomaterials and nanoscience? Because people say the carbon black was used about 100 years ago, fumed silica was there, and so many materials were there. Okay, probably at that time we were using those materials by understanding only part of the properties. Now, since we have a better understanding, what you can do, not only you can find the different applications, but you can probably tailor the nanomaterials based on your requirement. There's a bit of disturbance, some background noise, which will go otherwise. I'll ask these fellows. Please bear with me. Now, what are the properties in the change? Surface area is a physical property. I'm not talking about that. The quantum size effect, which will actually govern the electrical or optical properties. Okay, we'll take a couple of examples. Large surface area or large surface to volume ratio. That will also change your thermal sensing and absorption properties. And absorption will be quite a lot at NEERI. And the reduced imperfection, okay, that is also a factor of many properties, including the photocatalytic things, okay, and even the conductivity. The quantum size effect will decide the color conductivity of electronic properties, while the dispersion will impact your melting, cohesion, vapor pressure, solubility, sensing, and other properties as well. This is the way to explain what do you mean by change in the properties. And as I mentioned before, most of you are familiar with this. So this is for the benefits of the students. Then if you are changing the CDT nanoparticles, if it is CDTE, it should not change color for sure. Okay, we all understand. Unless you're changing the chemical phase of that thing, it will not change the color. Okay? You take any material, any damn material, okay? How it can change color if you are bringing it to smaller size. But that's the nanoscience where, as we understood, change the properties when you observe, that is truly the nanoscience. So you have the same material like CD tellurium or for that matter gold or the silver. They will to a great extent behave differently as a function of the size. Okay. This is the optical properties of gold and which has been thoroughly studied. And one of the best applications of nano gold is catalysis, where they are trying for like zero oxidation even at the room temperature. Okay. This is melting of supported nanoparticle as you go down your as I mentioned that your melting sort of point will also like change. And this is also sometimes a bottleneck or like the challenge or the problem because when we design a catalyst, sometimes you get a fantastic surface area, very high activity, okay? But if you're trying for a high temperature applications, quite often nanoparticles shows relatively inferior, like thermal stability. You need to have a compromise there. So these are the properties we include. Now, for the students, I used to take classes after 3 months teaching them nanoscience and nanotechnology. I used to ask them a question. like, which one is more important for those? I mean, I'm talking about the BSc grades or MSc students. A powder with average particle size of 99 nanometer or a powder with average size of 101 nanometer. So they used to get very, very sure about the definition of materials, and they used to immediately pick up that, sir, I will pick up a material which will have a particle size of 99 nanometer, and I will discard a material which will have a particle size of 101 nanometer. We should understand neither the physical properties nor the chemical or any other properties are going to change by a difference of 2 nanometer. Okay, so it's an overall range where for some materials you can find the property change below 20 nanometer. Sometimes it's only a convention to the students. Now, moving to the applications of nanoparticles, I picked up this from this gentleman. You can imagine, I believe another 100 or 200 things can be put into this picture. So, right from renewable energy to textile to biomedical healthcare, everything, probably everywhere you will find it, because nanomaterials are optional materials. So, wherever you are finding materials application, you can find nanomaterials. In addition to that, you can very well find a new application. So huge number of applications are possible with the nanomaterials. Only thing we should know how to exploit it. Now the next part is can it be misused? Like everything has or every coin has a two faces. Okay, like nuclear has been developed or designed for the energy purposes, for very clean energy purposes. It was like misused. Now, what is the impact of technology on society? Very generic couple of slides I'll give for the benefits of those who might be interested in this coordinated lecture. There are always intended impacts. Okay, we are discussing nowadays about the COVID or coronavirus. There are always intended impacts. Very good thing. Sometimes unintentionally, accidentally, we have some like adverse impact, and sometimes even intentionally. So you have unintended impacts. We call it. The virus was by mistake leaked from some lab and all these things, or anything was leaked. And then there are some undesirable consequences. So, in case of nanoscience or nanotechnology, for that matter, any branch of science, sometimes when you are exploring the new things, you might ignore the consequences, and we should be very, very careful about it. Okay. This I picked up. I'm a very strong believer that nanotechnology is a very, very useful thing. Okay, and as of date, there are very, very limited, like problems related to nanocomputers or nanotechnology. Okay, people call it there has not been enough research done to know what the biological implications of nano industry would be. Okay, there is evidence of suggest possible problems. Okay, and but there is a good amount of research being done. Okay, recently I found a lot of articles to see the interaction of nanoparticles with the COVID virus. Okay, how it can disinfect, how it can extract the RNA, and so on. Okay, these are the societal concerns. There are second order consequences, what is commonly known as. Okay, you are working in an industry, and suppose a country who is good at nanotechnology and suddenly he finds a lot of applications. You must be familiar that many conventional industry was really badly impacted with the new inventions. There's nothing wrong because you are improving the technology and you are reducing the environmental impact, and for all good reasons you are doing it. But unintentionally, a part of a section of the industry will get affected. Okay, and you need a new skills, you need a new industry. Okay, and there could be a narrow divide. Like we always say, there's a rural divide in India, or there's a like poor and rich divide. Similarly, there will be a technology divide. Okay, but these are we can't help it. In fact, there are a lot of very good studies in it, and I just picked up very few that how the nanosilica affects the aquatic life, which we dispose of or we discharge in the ocean and the water bodies, quite sometimes unintentionally. Okay, we use a lot of nanosilvers nowadays, and nanosilvers has been recognized as one of the best things for disinfection of water and many other applications. Okay, but now for last 15 to 20 years, there have been very convincing studies that you have to track down the fate of discharged nanosilvers, which could be very badly affecting the water bodies, especially water bodies. Okay. There have been very nice studies, in fact, and I was surprised when I was preparing for this lecture that People are studying and studied way back, almost 10 years back, ecosystem response to nanosilver under the realistic field scenario. So one lesson to learn that whatever you are using, you must take care that everything, practically everything, has a way to safely dispose of. That's what we learn at NEERI. So similarly, nano materials are fantastic. Okay, they can give you very good applications, but at the same time, nothing can be discharged, nothing can be disposed of casually or irresponsibly. Okay, this is how they project the growth of nano technology. Okay, and around this 2005 to 10, they call it an early adopter, and up to 2025. So this is the era we are going through where rapid advancement, okay, and commercialization of nanomaterials and nanotechnology is taking place. And we are witnessing, fortunately, it is a true prediction, okay, which has done it. So these are the typical nanoparticle risks you might have heard also, or like sometimes there is news also in the newspaper that some industry is facing some problem because they deal with the nano carbon particles or other nanoparticles, silica particles. Okay, these are like typical particles. So nowadays it's very easy to understand because in India we talk too much about the PM emissions. Okay. So similarly, when we have the ambient PM emissions from different sources, the combustion of the vehicle, in what is known as an occupational hazard, in a factory where if you are producing nanoparticles or if you are dealing with the nanoparticles and I would say the processes are not so optimized or so controlled, then there is a possibility of exposure to these things. Then risk to human, we can understand these things. They can be pretty damaging to you, in fact. Okay, so there are many policies nowadays to ethical use, number one, careful use, number two, and third is the safe disposal of nanoparticles. Fine. So these are some of the risks. Again, the toxic waste. Okay, there are few imaginary things like they call the scenario when they feel that it's pretty hypothetical where they expect that it could be so reactive that it will start replicating like biological nanoparticle like a virus and all that. Well, this is one thing which bothers everybody because today you can say that nuclear weapons are not so easy to construct, okay? Because they need some space, they need some facilities. If the nanotechnology can be badly exploited in the wrong way, okay, they can probably lead to like production of mass destruction, weapons of mass destruction in a very small place where it is very difficult to identify. So we have to be very careful. There is a pretty like interesting lobby because of the anti-nanotechnology. I don't think so. There's not. So do we really need nano after this background? Yes, sure. Okay. So we definitely need nano. Now we'll see that like what are the useful things, couple of useful things which I can explain to some of our work also and general science. One is what I have written is to interpret the natural processes and learn from them. Okay. Again, I'll take a very recent example of coronavirus. You can imagine this virus is omnipresent. Okay, it's maybe in my room also around me, but I can't see it. Okay, then how can I interpret those things unless we understand the nanoscience, the biological science, and also we should have the proper tool to study these things. Okay, so one of the biggest advantage they call it with the nanoscience development and nanomaterials in particular. The characterization tools have shown revolutionary advancement in the last 20 years. Okay, the strength and like the efficacy of the machines like the PM or HRTM, the DLS based even simple techniques have gone far ahead, which is helping us to not only look into the nanoscience or nanoparticle per se, but they are also helping us in the understanding the natural processes which are happening and do happen often at the nano level. Okay. Second is to judiciously use the resources. Okay, I'm sure many of you must be aware of the term atom economy. Why they call it atom economy? In a chemical industry, if you are able to take care of every atom or molecule of your raw material, and if which is theoretically possible, the efficiency of your reaction or yield of your reaction is 100%. Okay? What does it mean? You will not produce any byproduct. Once you're not producing any undesired byproduct, half of your environmental problems are gone. You don't have to worry about it. The benefit, obviously, your product quality will be good, will be less impurity, and naturally the yield will be 100%. So you can talk atom economy wherever we are talking about reacting to the each and every atom or molecule level. Okay, so that your resource efficiency goes up. I'll come to this later on. There will be no environmental issues mainly. Then many new properties will be discovered because of the science. Can virtually change the applied science dramatically. I will slightly change this sentence that it has virtually changed the applied science. Okay, quite dramatically. Already it has been done in fact. Okay? And as we are facing the new challenges almost every year, okay, we need to have a very strong fundamental understanding of science, and also we need a very good like strength in exploiting these new properties of nanomaterial so that we can meet those challenges. One of the challenges I'll take about related to water. This is what we published last week actually. It doesn't have like a direct relationship, but like what we have tried to point out here in this publication, Science in Total Environment, that there has been very good publications, huge number of publications related to COVID and Corona. Okay, and people have already established that what is the stability of this virus, okay, on different surfaces? Let it be metal, especially like copper, steel, glass, okay, fabric, vegetable, everything has been done. We quickly realized that all these studies, for obvious reasons, have been done on a clean surface. If you want to study the copper, naturally you need a clean copper surface. Only then you can sort of conclude anything. But then we highlighted in this that there is a need to understand what is the interaction of particles which are only present. Okay, in reality, you cannot get a surface in general atmosphere where there are no particles are present. Okay? Particle-free surfaces are not there. So we just highlighted this thing that it is not only that. Just give me 1 sec. I'll ask this guy to stop drilling. Just 1 minute. Okay, we'll go ahead. So, how these particles, especially the nanoparticles, they like they can affect the stability of coronavirus. The second thing, if the virus is is supported on these particles, and this particle become airborne. So at the same time, the same particle can sort of increase the fomite transmission. So this is how many of the scientists are working. In fact, I found paper from EIFR and many. This small cartoon, in fact, how nanotechnology or nanoscience can be used. In fact, it's very, very useful for everybody. Like these are why we need radically new technologies. This is how our population increased. Okay, now it is shooting up like anything. Okay, so naturally population increase means increased consumption of water, food. Okay, the resources, lot of new pollutants, lot of environmental changes, okay, and lot of new technology or the need. So if you see traditionally, what are the revolutionary forces? We started in the 19th century, mid of 19th century. There was a revolution for the textiles, followed by transportation, especially the railroad. And then the automobile came, okay, which was revolutionary. And then computer was introduced in India probably around 90s, while abroad it was in the 70s. They say up to 2025 or 2030 there will be saturation, while the nanotechnology will go on for next several decades because we need to find a lot of applications in drug, textiles, and whatnot, you name it. Okay, so this was the growth curve of nanotechnology. I thought I'll show you the video, but it's a bit complicated, so I'll just skip this thing because by now you must have clearly got a good idea about the science and general idea about the nanotechnologies. Okay. Now, first we'll take up a couple of things related to energy-related applications, and then we'll move to one or two applications that are related to environment and which actually we are practicing in our lab. I hope you are able to hear me. Can somebody confirm? Hello?
Yes, sir. Yes, sir. It is audible.
Fine, thank you. So, if you talk about the Indian scenario, if you read the newspapers, you'll be a little surprised, especially if you're not from energy domain. Okay, the energy demand is increasing because our economic development is on a pretty good path, except for last couple of months, in fact, because of the COVID. So, but suddenly you'll realize that the India's coal import is rising. Okay, and then the next day you'll find that there's good news about the solar. We are one of the most aggressive countries in the world for solar installations. Okay, then the third day you will read something about the thermal power project. Okay, they are facing stress. So it's quite contradictory that we are working on say solar, and then suddenly we find coal is also used. Coal is why it is happening. Okay, so 10 to 20 years ago, many of like my age, okay, if 20 years ago, if you talk about the electricity or energy, it actually means provide electricity to the rural homes where electricity was not there, or minimize the load shedding. That was the only concern. And you see how things changes. In 20 years, today, energy also symbolizes, very unfortunately, pollution, especially the GHG, like climate change, renewables, which is a good news, regional conflict, and even the country's economic jerks. So energy has become very important in both economic and environmental point of view. Okay? This is a bit of something interesting you might find, in fact. There's a rate of change in the global primary demand as per the International Energy Agency, IEA, it's the most credible agency. You can see here a sudden drop, which is because of the COVID. Okay, COVID pandemic has resulted in the drop in the energy demand. But if you see the overall, okay, this is from the VP Energy Outlook. If you ask anybody who is again not familiar, some student, that the way we are going towards solar and the renewables, what do you predict in 2040? Okay, this is how it will be. Your energy demand is going to go up, but if you see in the right side of the figure, okay, where the renewables, which are increasing, they were not existing before, and it's going up, and this light brown is showing or orange is showing renewable, okay. But can you believe that the coal is also increasing, the oil is also increasing, and the gas, which is all fossil fuel, are increasing significantly. Why it is happening? This is happening despite the very impressive growth in the renewables for one single reason, that despite the very handsome growth in solar and renewable, your overall energy demand is increasing like anything. That is basically compensated. You need more solar, but at the same time, you need more coal because so much of energy you need cannot be managed by solar. Okay. So here comes the concepts of energy efficiency, reducing the use of the efficiency or wastes of the energy. So they call it a COVID pandemic has done only two good things. One is related to energy, second is related to the environment. Otherwise, everywhere it is evolved. Okay. This is the impact of COVID containment measures on weekly total energy demand, which was pretty much reduced during the full lockdown, and now it is again picking up. And that was one of the reasons for why the pollution was less. This is something called load factor. Okay, so usual load factor should be 60 plus. So you have capacity for 1,000 megawatt or 10,000 megawatt. Okay, installed capacity. At what load factor you are working on average? Because if the load factor goes down below 50% or 55%, the production is not very commercially viable or otherwise also. So now there's a very bad shock when it comes to the energy. And this prompts everybody to look into not only the new ways of energy generation, but also to the energy storage. Okay, and how to be prepared for the next jerk if it all we get, not for this, for anything else. So this is I picked up a couple of slides. So this is not my work. Okay? This is for the benefit of all the people. These are some good reads about applications of nanoscience on both renewable energies as well as storage. Okay. Again, you can go back to the fundamentals that like increasing the surface area, okay, the nanoparticle interface as well as the size quantum impact. Okay, they offer the new opportunities that something which was not feasible earlier with the efforts of last 20 years or 10 years. Okay, those things are becoming because like it's very fundamentally it's easy to understand. You talk about the energy storage. Now, what kind of energy storage you have in your battery? It's very small. Okay, and you can expect that this to reduce by another 80% or 90% in the next generation batteries after 10 years. So this is really revolutionary. Okay. Well, a couple of things like catalysis by nanoscale material is very useful for fuel cell application as well as not only energy storage but the conversion of those energy storage systems, like for example liquid organic hydrides. Okay. Then using interface to manipulate energy carriers. Okay. So this is a pretty good branch of physics, I would say. Linking structure and function at the nanoscale, assembly and architecture of nanoscale structures, and then comes the modeling and simulation part. What is a bit challenging as a chemist, I feel, is whether these things are scalable. Okay. So that becomes a second challenge. Initially, you have to prove scientifically, conceptually, and then once you go for the industrial production, the synthesis methods takes the major role in fact. Red cell cell, all of us know the entire photocatalytic revolution and even I would say EV revolution is based on the nanoscience and nanomaterials because the materials changes properties and that allowed many low cost and stable materials, okay, to be exploited for not only photocatalytic water splitting, which I'm sure somebody will talk about those phenomena, but a material which may not show the photocatalytic properties, if you tune it properly, it can enhance its photocatalytic activity. Okay. Hydrogen storage materials, I have already mentioned about it because always remember that you carry a 40 liter of diesel or petrol. So you never worry about it, but that weighs, okay? There is a weight for this thing which you are always carrying in your vehicle. So if you want hydrogen to be carried or electricity to be carried, you need a battery which should not weigh much. Suppose you have to carry a battery worth 200 kg. So it's a load of 3 to 4 people you are carrying in a car without any for the sake of fuel. So we always forget these things, but these are the basic things for which you need a very high energy density materials, okay, for which it is being very nicely exploited. And second thing, if you are working in a system, something like LOH, liquid organic hydrides or metal hydrides, you need to also worry that how to regenerate those things and how to release your hydrogen per se. Okay, these things are very important. Where it is not only the nanomaterials, but the nano reactors are also playing an important role. So this was a generic picture about tapping the sun's energy, and many people are now going to the next level where like what they're trying to do is to understand how to best exploit it. It's now a fairly good amount of technologies are there, although people are still struggling to increase the like PV conversion and also the conversion efficiency to PV, which is around 80 to maybe less than 18 to 20%. And there are claims for the 40% or 50%. But whatever the mature technologies are there, people are also trying how best it can be utilized. So there is a concept of energy islands, okay, where you need to map the whole thing. Then you can try many potential ways of generating energy and how best you can utilize it. That was a bit conceptual rather. So photovoltaic solar cells is one thing which is very beautifully exploited with nanoscience and nanomaterials. And all of you are quite familiar with this. There is a new generation of PV which are coming into the picture. In fact, okay, there are a few disadvantages, less efficiency. People are coming up with perovskites and new generation of organic hybrid materials which are showing excellent efficiency. There are some issues about the stability. some environmental concerns, but I'm sure those are being taken care. There are flexible solar PV, which will have very interesting applications because nowadays you need a small UVs, not always you have enough space or enough frames to do that. It can be exploited very well. This is very typical, and I probably should have shown you something where what kind of energy generation efficiency we have. There are two things. One is energy generation. Say you have a coal-based power plant. How much is the efficiency? And then we all understand that this energy generated in the form of say electricity, it will be transported, okay, and there is a transmission losses, and when it reaches your home, then you are going to use it, say for a air conditioner or for anything. Then again, you should understand what is the efficiency of your air conditioner. Sometimes you call it 50% or 60%. Your power plant is giving you the energy of 35%, then there are transmission losses. And when it comes to your home, the devices which you are using again gives you 30, 40, 50% efficiency. So you need to quickly understand that although we are talking about the CO2 is a problem, okay, we are talking about the targets where we are talking we are reduced by 5% to 10%, it will be quite good. But we need to understand that almost close to 85% of the CO2 which is going into the atmosphere, that is because of the losses. We are not actually using it. Okay, losses during the production of energy, losses during the transmission, losses during its use. So there's plenty of scope. Okay, plenty of preventive options can be done where you can improve the efficiency. Let it be the energy transport efficiency, energy transmission efficiency, generation efficiency. Like we call it a fuel cell 80%, but before that, what? Once you are able to increase that, you can hit a overall efficiency of 30%, 40%. It's very ambitious, but it should ideally take care of the problems or many, many problems. Okay. Then, as I have already mentioned about these things, and I could see in the program that there are people who are going to explain about it. Okay, so I'm going to skip it. Now the windmill. Okay, the windmill blade. Okay, there is a lot of nanomaterial goes into that. Okay, the kind of material strength as well as the many parameters in the windmill, which where people are using a lot of nanomaterials, including the CNTs. This I was already explaining you that hydrogen powered vehicle will require a lot of use of the materials, especially for like two things. One is storage, and second thing is fuel cell based generation. Okay. So, what are the challenges and opportunities? One is the mass production of nanomaterials with the good quality. Okay, in the sense, if you are producing the nanomaterials in the bulk, they should be of the same dimension. Okay, of the same quality. High heat flux materials are also coming up. Okay? And well, there are many breakthroughs already, but the people are claiming that many breakthroughs are on the offense. They're coming in. We can definitely expect. Okay? So now coming to the environmental applications, this is only about the sensor, and you can imagine what all kinds of sensors are there now. Okay. I mean, there are hundreds of sensors will be required. In environment field, we can understand that so many revolutions are going on. And why do you need them actually? It was so difficult to bring the water sample to the lab, preserve it properly, and get it analyzed using very complex procedure, pre-treatment, and all that. And the same job is now done by the sensor on the field. Okay, the real-time data you can generate. It is rather mandatory nowadays to have these kind of sensors for wastewater related data, and the industries you can imagine directly connected to like wireless systems to the cloud-based system to the central pollution control board. That's the kind of a revolutions we are seeing as far as sensors are concerned. There is an industry 1,000 kilometers from the central pollution control board. They have some sensors installed. It is mandatory, and the data is directly generating and going to that. Say, for example, River Ganga or Ganges, there are so many monitoring stations. There are wonderful applications of sensors which are very much required. For example, air pollution, indoor air quality. You talk anything. Okay, you talk the hospitals where they are worried about the indoor air quality. Okay, so there was not. It was not easy. You have to take a like a high volume sampler or low volume sampler, do the measurement for 6 hours, bring the filter paper, bring it in the lab, and do all kinds of things. Then you will get one reading. that job probably can be done by sensor. Now, what are the environmental applications of nano we are pursuing in our group and a couple of other groups at NEERI? What are the advantages? I mentioned high surface area is a big advantage. Okay, once you have a high surface area, naturally you need a small amount of material. So the cost of the material for treatment of any environmental pollutant goes down. Okay, you need to understand that nobody wants to invest a single rupee on environment. Okay, because if you have an industry, there's a cutthroat competition for the lower cost of the production. Somehow you are managing that. Okay, somebody is producing at 100 rupees per kg, you need to make it to 90 rupees per kg. And at that time, if somebody asks you that why don't you install this pollution abatement equipment, which will increase your cost to 105 rupees, nobody will accept it. No one. Okay. So you need to create a material and the system for environmental pollution control, which are low cost, low operation. Okay. So material requirement should be less. So you are trying to suppose treat the water pollution with absorbent. So naturally, if you have nanomaterials, the surface area is high. The job of 100 gram will be done by just 10 gram. Second is lower environmental impact. As I have mentioned you that everything is fine, but then how are you disposing of is very important. Given a lake to be decontaminated and somebody comes to me that there's a big lake which has got some arsenic pollutant or some spillage has got there, okay, which we need to treat. And suppose we estimated we need a 2 tons of material to remove all those hazardous metals or pollutant from that lake. Fine, we have done it. Now, what is to be done with that 2 ton of material which is full of that pollutant? Okay, that is a big thing, and that's why I have written a word LCA life cycle assessment. So that has become a very good tool, very useful tool, okay, to even assess that what you are trying to do, whether in an overall sort of scenario, whether that is useful or not, because there is always indirect impact there, okay, which we often ignore. We have seen the sites in many parts of the country where you will find the exhausted defluoridation media right next to the defluoridation plant. You go to the village, there's a nice hand pump attached defluoridation system which is taking out the fluoride from the water. And just you will roam around and you will find there is a dump where they are throwing the used media or exhausted media. Now, suppose there is a water, little bit of acidic water, okay? That water will again release the fluoride from this media, exhausted media, and there's all the possibility this fluoride will again go to the groundwater. Okay? So we need to understand that the process should be complete. Okay? Like LCA, we all understand is a cradle to grave concept where we need to find out what is the cost, what is the material, what is the resources, what is the environmental damage you have done to generate that material, what are the transportation cost, what is the cost of the fabrication of your device, what is the O&M, how much is the energy required, and just do all these things and then add these disposable things, how safely you're disposing. Only then you can say that I have treated 5,000 liters of water using this much of energy, using this much of resources. It's not that easy that we will say, yeah, I spend this 500. Okay. So these LCA concepts are coming up and taking up really fast. Okay. So now we need a new properties to handle new environmental challenges. For example, GHG was not a problem. Low temperature CO oxidation, was a big issue. But now that you have at least 3-4 candidate catalysts which can oxidize CO at low, even room temperature. Cleaner energy, we have seen how many options the nanotechnology and nanoscience or nanomaterials for that matter even has. What are the challenges involved? One is I have already discussed the health and environmental impacts of nanosize of material. We have seen people are looking into the fate of nanosilver, which is used for water purification and many other materials. The process cost of nanomaterials bulk synthesis it has to be reduced. Okay, one of the very key challenges is separation of nanomaterials. Again, I'll give the same example. Your lake is contaminated. Instead of 1 ton of material, I will spread just 10 kg of nanomaterials into that. Now, my challenge will be how to separate that. If I have a pellet and if I have a material like nano size, I will have to filter the entire lake water or try something or maybe some magnetic techniques if it is an iron-based material. Otherwise, separation of nanomaterial is quite tedious as well as energy intensive because we have to use a membrane. So if you have to use the membrane for separation of nanomaterials, you can use the membrane for pollutant removal as well. Why to use it? So now what you can do, there is another example I have mentioned that there are very good candidate catalysts we explored for the auto exhaust applications, but they are not thermally very stable. Auto exhaust temperature can shoot up to 700-800 degrees Celsius. Your catalyst should be stable. So now one of our interests is to explore the properties of supported nanomaterials. You got a very good adsorbent. The only problem is how to separate it from, say, wastewater. You can support that material on some aluminum beads or pallets or any other structure which is porous, like beads and all these things. But what is interesting here that you talk so much about the nanoscience and nanoparticles that their surface to bulk ratio is very, very high. Now, if you are supporting those nanoparticles into these beads, what will happen to their properties? They're likely to change to some extent. Okay, so there's a lot of scope, and many people are working on this, how to optimize these things, and there are many commercial applications already. So we little loosely, but we use something called nanostructured materials. Okay, it's not necessary that the final size of our particle will be 20 nanometer or 40 nanometer. Sometimes the final particle size may be more, okay, but still we can get some advantages. Zeolite is a very typical thing. The particle size of zeolite could be anything, okay, but it has got an order structure. It has got a micro surface area or micro porosity, which gives you very, very high surface area. So not necessarily that a zeolite particle is more than 100 nanometers is a useless material. They are most useful material. Now, oil spillage, we have recently seen some of the neighboring countries, there's a huge oil spill, and they are using photocatalytic like copper tungsten oxide based particles. The advantage there is like you need something which can be dispersed, it should not be harmful to the seawater, and at the same time, it should use some natural resources like sunlight to degrade it. Okay, that's the demand of an application. Okay, if oil spill is there, the best application is you spread something and in say 48 hours with sunlight using photocatalytic activity or photocatalytic oxidation properties. If it is taking care of or decomposing it into say CO2, okay, you solve the problem instead of like. And sometimes it is possible to design a material which will have both the properties. It can attract the oil properties, okay, typical like hydrophobic property, and you can generate the hydrophobicity as well as the photocatalytic property. So a bifunctional material, okay, or hybrid kind of a material can be done. But again, as I mentioned, the very interesting literature is available where they are combining two nanoparticles to get hybrid property, and then they find some change in the property, which is very obvious. Because now your size is changing, your surface to bulk ratio is changing. So there are very good literature depending on the thing. Radioactive waste cleanup, also there are very good applications of the nanomaterials. And I heard that even in Fukushima or many other disasters, they use quite a lot of money. Okay. So when it comes to the, we have seen the energy and then we have also seen energy environment. When it comes to the energy environment nexus, like there are two issues we understand. One is the greenhouse gas emissions, which are primarily because of the CO2 and to some extent the methane and some other GHG gases, which is a global issue. But there is a fairly significant amount of conventional pollution which is happening, like air, water, soil, and sometimes they are local issues. Okay, because fly ash is also locally gets deposited. Water pollution is pretty local, and the soil pollution also. But sometimes it happens that because of the GHG problem, these problems are ignored. Okay, but it should not be the case. And as we mentioned, the indirect impact of life cycle assessment is very, very important. Sometimes the group which works in NEERI and a couple of other CSIR labs, they found that based on the practical applications, they are even trying to strengthen these tools. I'll quickly give you one example. For example, if I ask you what is the sort of carbon emissions or carbon footprint of solar PV, if you ask a schoolboy, he will say it is zero. But we all understand that it cannot be zero because we need to spend a lot of energy to produce these photovoltaic panels, and that's a high temperature process. then you need some energy to transport this photovoltaic panel. It was so high during the first generation of solar PV that there are articles claiming that if you install a PV and if it is working for less than 5 years, okay, for some reason it gets damaged, you haven't done any good. Why? Because so much of energy has gone and CO2 emissions were released in the production of this PV. Fortunately, now the new generation of PV requires relatively much lesser, in fact, significantly less amount of it. So, second example is we say coal-based power plant. So we can even calculate. Anybody can calculate if I have burned 1 ton of coal, C plus O2, how much of emissions I will get of CO2. Okay, and then we can say for generating 1 megawatt of power, I use this much of coal and this is the CO2 emissions. How about the CO2 emissions released during the mining of the coal? Because we are going to use a lot of diesel vehicles and other equipment. How about transportation of coal to the power plant? How did you transport? Again, using diesel dumper and all these things. During the transport of the coal, there was a lot of coal powder which was released in the atmosphere. So all these things are becoming an important aspect of life cycle assessment. Okay? So if you feel that this energy option is clean, you need to put it immediately to the LCA. And only then you can say, oh yes, it's relatively cleaner. Now, a lot many things are going into CCUS, what is called as the carbon capture, utilization, and sequestration. Okay, and one of the best ways to take care of the CO2, if you can convert CO2 into fuel. Why? Because majority of the CO2 is coming from the fuel. But the condition is for converting CO2 back into the fuel, you should not release too much of CO2, or you should not spend too much of energy. Otherwise, there's no fun. If you're converting using a high temperature process of CO2 into methanol, and that methanol you're using in a fuel cell, but in the process, if you release more CO2, there's no fun. So one of the most ambitious reactions, or sometimes some scientists used to call it a holy grail, is to convert like CO2 into fuel by using solar energy. Okay, or you can convert water into hydrogen by using solar energy, that is photocatalytic water splitting. These are some of the most ambitious reactions, but there is wonderful advancement in that. Now, the second issue is what can be done with the CO2. As I mentioned, you produce so much of CO2 that you come up with an idea that I will convert this CO2 into something, some material, okay, which you can use, quite similar to the fly ash. So you can convert, you can make some kind of a catalyst using the fly ash. How much of fly ash you are going to use by converting fly ash into catalyst? That's the question. So how much of CO2 you are able to convert? Otherwise, today CO2 is a problem. Tomorrow, if you convert it to a plastic or anything else, that chemical will be a problem. So you need to convert CO2 in something which is required in a huge volume. For example, fuel. Okay, and then you need to look into what are the environmental consequences, what the economic, technical feasibility of this. Okay, so one of the key reactions is CO2 reforming of methane. Okay, so there have been a pretty high temperature reaction, and there has been a lot of catalyst development in this area. Okay, so there are like dry reforming, steam reforming kind of reaction, which can give you the syngas, and syngas can be converted into many useful chemicals. So here in my group, we are working with one of the, in fact, EMRD grad only, so it was saying wonderful such associate working with us. So there we are trying to develop some new catalysts which are more stable and which can do this reaction at relatively low temperature. Okay. So nickel-based reactions are very popular, but the only problem is both deposition and stability of this nickel-based catalyst, and the reaction temperature is quite high. As I mentioned, you need to perform these reactions at low temperature. There, the challenge is you can improve the surface area, you can reduce the amount of catalyst required, but your catalyst, nano-catalyst especially, needs to be thoroughly stable. That's a big challenge where people are using different supports on this. And for considering the fact that we have pretty interdisciplinary participation, I'm not going to go into the details of these things, but if you are interested, we can discuss separately that how we perform this reaction, how we synthesize. Normally, the synthesis procedure we are following are pretty simple. Okay, those are either impregnation but I personally prefer incipient wetness method, which can be performed in any small lab, okay, and which can give you fairly good dispersion of nanoparticles of these catalysts. The incipient wetness method can be optimized for wonderful catalyst preparation. Okay. The next is water treatment. Okay. So sensing and detection, as I mentioned, has a lot of prospects where nanomaterials and nanoscience can do wonder. And nowadays, we have a sense of arsenic or fluoride, which are commonly used. And for treatment and remedial, most of the times they are using absorption and also the functionalized membrane, where a lot of nanoscience and nanomaterials goes, and of course the pollution prevention. Okay, so sensor-based technologies are pretty mature for fluoride. If we use it, the only thing is we need to. I personally feel it's a wonderful idea to have indigenous fluoride sensor or fluoride electrode, what we call it. Cost a lot. Okay, so there are very good prospects in doing that in many labs. It costs few tens of thousands, and the shelf life is just 6 months. So there is a prospect that we should develop these sensors, reliable sensors. Okay, desalination, as all you know that water demand is going up, especially for drinking water, and I'm sure those who are from South India they already know that Chennai has got a huge plan for the desalination of seawater. They are already getting a fairly good, like share of their drinking water from desalination. Okay, but as the salinity of seawater is very very high, okay, it requires a lot of energy. Okay, and it has a huge reject, probably close to 70%. So there are a few techniques and technologies for desalination of water which are based on a nanoporous membrane, and I wish they should either they of like immediate in near future. Then just something from my lab that some low cost nanomaterials we are using for selenium removal from water. Okay? This is something interesting figure that if you Google and put a fluoride removal technologies, I tried this few years back. In fact. Now today you will get even very high. This is 3.5 billion results on fluoride removal technologies. But even today, there are more than 200 million people affected. What does it mean? The message is there is a lot of research going on, but there is a poor translation of laboratory-based developments to field, okay? And the challenges related to implementation, especially operational and maintenance. There was a beautiful paper from Jadavpur University claiming that the rural water technologies normally have a life of about 18 months. Okay, so within 18 months, more than 70% of the plants were defunct. They found in a survey, which is really bad scenario because it's hard and money going to break. Now, what is selenium? Selenium is a new pollutant. As I mentioned, that with the environmental impacts, okay, and many reasons, now we are getting what is known as the emerging pollutant or the new pollutant. So it's a micronutrient nowadays for like for immunity boosting. They say you should also have some syrup in which zinc is there, selenium should be there. Okay? But very unfortunately, you need it in a very, very small dose, roughly 25 to 35 microgram per day. Okay? And if it is increased, which is already increasing in Punjab and Haryana, and the government of India has already put it selenium in the list of emerging pollutant, then it has got a pretty bad health implications. Okay? So why nanoscience nanomaterials? As I mentioned, because like one of the field challenges related to these technologies is you go to the say rural areas where you install a water treatment plant, drinking water treatment plant, and you put adsorption media, say 10 kg of adsorption media. Then after some time, you need to go and regenerate that media, which is a challenge, which nobody goes back. Okay, if you want to create a domestic water treatment device, you need to give them say 1 kg of material, which will last about 2 months. Then what to do with this material? As I mentioned, you can't throw it. Otherwise, you have to bring it back again, regenerate it. What nanoscience and nanomaterial do here? If you see the typical activated alumina-based adsorption or adsorbent of fluoride, okay, say 80 mg fluoride removal per gram in 50 cycles. The capacity is 2 mg per gram. And then you need to regenerate. And you can regenerate it for say 40 cycles, 50 cycles. So in the entire lifetime, 1 gram of alumina can remove only 80 mg of fluoride. Okay, then there is a regeneration cost, there is a regeneration waste. Everything is there. What happens if you are using a nanomaterial? Maybe if you can increase the adsorption capacity from 2 to say 20, which is very much possible, I believe. What you have to do, you can in fact give 20 gram or 50 gram of material or a cartridge or a sachet to a person, okay, and he can use it for 6 months. So instead of 5 kg and regeneration, now you are dealing with 50 gram or 100. So we tried some iron-based materials, iron oxyhydroxide, which can be synthesized in the lab using very simple technique. Okay, there is a like reduction process which can be controlled, and you can get beautiful nanoparticles of like lepidocroside or other phases of iron oxyhydroxides. So this is done by one of actually PhD student Professor Shriram from University of Hyderabad. He spent about a year with me. He's from Yemen, in fact. So you can characterize these materials using the techniques, simple techniques, spectrogram, yeah, spectra. And if you are interested, you can go ahead with the further little bit of advanced characterization, but it's not so difficult and everything can be done pretty well using the commonly available characterization technique. Then we tried to use this material for separation of selenium from water. And the results were so good that with the zero point 0.2 gram, less than 0.2 gram dose of this material for 1 liter of water, okay, where we normally need a 2 gram of material, okay, so almost 90% reduction in the weight was possible, okay. And then we, tried another phase at ignite, which was also equally effective. Now, what we feel that if you have this kind of a domestic filter, which was very common before, okay, just to remove the turbidity, you can put additional one, some bottle which is made of food grade plastic, okay, and you can put this material so that finally after filtration, the material, the water will pass through these materials. And if you have a very high capacity, okay, I think few tens gram of material will be sufficient for 6 months. So this is one of the things. Groundwater, as I mentioned, like wastewater of the lake, where the separation of nanomaterials is very difficult, magnetic nanoparticles can do wonders because their separation is quite easy. Okay? So if you are able to magnetically separate those particles after doing their job, okay, it is possible. And there are a lot of experiments being done even for treatment of groundwater. Last leg of my lecture, we are left to hardly 15 minutes. Maybe I'll take 10 to 12 minutes and we will for some discussion. It's catalytic applications. So we are exploring a few catalytic applications. One major application I'm exploring is diesel soot oxidation. The second is the oxidation of volatile organic compounds. Okay, and then we are working on incinerators. We must have read about the incinerator for sanitary pads. Now we are coming up with the biomedical waste incinerator, where we are also using catalyst for emission control. This is a beautiful application of like nanotechnology, nanomaterial, but this was invented somewhere around 70s. Okay, the catalytic. The beautiful part of it, like if you really calculate the amount of exhaust coming out of a vehicle, the volume is so enormous that if you want to treat this exhaust components, for example, carbon monoxide or hydrocarbon, okay, or for NOx, you need such a huge surface area because that exhaust flow sometimes goes 100 liter per second. Okay, such a huge area. So they initially estimated, this is also considered as one of the beautiful applications of chemical engineering. Okay, why? Because initial calculation showed for 1.5 or 2 liter of engine, okay, car, you need surface area close to a football ground. Now, how to do that? If you have a car for emission treatment, you need 5 cars. So that big of emission, like controlled devices, catalytic devices. Then came the invention of honeycomb structure. So these ceramic honeycomb structures gives you the highest geometric surface, but they need a high thermal stability. These are sintered materials, so they cannot give you the high porosity. Okay. So what was done, if you can see here, this is a honeycomb structure. On the honeycomb structure on their wall, there is a coating of aluminum. And this aluminum is a high surface area aluminum. And typically, in say 1.2 liter of catalytic converter or 1.5 liter of catalytic converter, you you can eventually generate a surface area worth a football ground, which was required. So there comes the nanopore concept and like the concept of enzyme. Because if you have small pores and if you want to put the catalyst on that, naturally these catalyst particles have to be very, very tiny. Okay, this is one of the best application of it. Now, what a nanoscience is doing in this area? Fortunately or unfortunately, majority of the catalysts in auto exhaust emission control are noble metals. They're platinum, palladium, and rhodium, and all of us know they are rare earths. Okay, they are actually very expensive because of their limited availability or limited resources. So we need to use it very, very judiciously. And there are new applications in the field cell. So their demand is going up. Okay. So one of the ways to do that, if you can disperse them, further, okay. Right now your particle size is something, yes, of course, you have to take care that your properties are not changing. Okay. Or another approach, if you can generate similar properties using non-noble metal based like transition metal catalyst. We're working on both on reducing the amount of noble metal and finding an alternate to the noble metal. And one of my colleagues, Dr. Sonawane, so we worked together for a while. Like you already have a small particle of these nanoparticles catalyst. Okay, but as you understand that catalysis is a surface phenomena, the bulk volume is, we call it a dead volume. It's of no use to us because my gas cannot enter the particles, say, center. Okay, it cannot enter. So if you can reduce this amount and prepare a hollow structure, okay, sounds very easy. The challenge is you need to create a hollow structure of few tens of nanometer particles. They're already small, but if you have a method and finally you come up with these kind of a hollow particle, then what you have done, you have taken out almost 60% or 70% of the bulk out of it, and you have saved a lot of global matter. So this is a beautiful application of a synthesis process or synthesis method, synthesis advancements in the nanoparticle science, and we were able to do this pretty well. Okay. Then we have tried some transition metal-based oxides, and again, we use the concept of nanoscience, where we worked on nanoparticles. Okay. This one was done with the Vivek Kulshitwar of KIFR. And one interesting result I'll show you here that yeah, there are two interesting results. One is we found some platinum nanoparticles and we went into analyzing it in a bit of a detail. And later on, we found it cannot be controlled. At least we were not able to control. We just tried the different methods. Okay, and in one of the methods we found that sort of 220 plane or 200 plane, if it is predominant, that has given us good catalytic activity. So shape tailored catalysis, all these things concepts are really good. And then we could also prove that yes, with the same amount of platinum, okay, if you have planar 220 nanoparticles, with the same amount of platinum, you get a better activity. This is another interesting thing where we synthesize a nanoperovskite using a hydrothermal method. And when we checked, we characterized those relatively small particles. When we checked for the activity, what was interesting for us, the synthesis which led to the nanoparticle showed a better activity. But that was obvious because now I checked the surface area and it was higher surface. We immediately correlated because of the high surface area, we got a better catalytic activity. What we did, we normalized the catalytic activity by plotting the surface area. Okay, we normalize against the surface area. That take care of the enhanced activity because of the surface area. And the second plot here, you can see still the catalyst was showing a high activity. What does it mean? The enhancement in the catalytic activity was not only because of the enhanced surface area, but there was some property change or activity change which cannot be explained only because of the surface area. There we discussed that this is probably the advantage of some change, some nanoscience-based change in the catalytic. I'm not going to go into the details because of the short of time, but we use these catalysts nowadays to prepare catalyst-coated brick. We call it a honeycomb support and the diesel particle filter. This is the diesel particles, which is becoming a cause of concern from the vehicle as well as genset. Okay, and these are very poisonous because the hydrocarbon gets deposited during the time it travels in the exhaust system. Okay, and these hydrocarbons makes it carcinogenic. So it affects your lungs and it also induces cancer. There are filters which are commercially available. You can place a filter in the car, diesel car, and it will trap all the particles. The problem comes after all the particles get trapped completely, and there is a back pressure. Nothing can get out of this thing. So you need to remove these particles. You need to burn it, and that temperature is quite high, close to 600 degrees Celsius. While the diesel exhaust temperature is 200 to 300 degrees. You can design a catalyst which can reduce this oxidation temperature or combustion temperature of the fluid from 600 to say 400 or 300 degrees Celsius. We are trying quite a few catalysts, mostly even non-noble metal-based low-cost catalysts, or promoted by a small amount of noble metal as well, platinum. These are some catalytic evaluation facilities, lab scale facilities we use to screen the catalyst. We can simulate a little bit of exhaust composition in our lab and run the catalyst. And then I used to normally evaluate the select catalyst from band scale facility at Kyushu University, where they have a diesel engine cut here, and we can divert an exhaust which will pass through the catalyst, and you can analyze like CO2 formation or superoxidation temperature. This is a few things of operando studies where we did some mechanistic aspects, okay, where we can see what is happening through in-situ IR. We published quite a few papers on this legal superoxidation catalyst. And finally, what was interesting that we prepared some prototypes. We got hold of ceramic supports using some lab-based techniques. We did it. And finally, we got it evaluated at the lab of Professor Avinash, a good friend of mine and collaborator from Nagpur, who I call it a single one-man army, runs almost 8 engine diameters with all facilities. And we could prove that even without using noble metal or using a small amount of noble metal, we can achieve comparative CO oxidation, okay, as compared to noble metal based catalyst. And then for scientific interest, if those who are having, we always love to publish, of course. And we did an interesting study where we sort of studied thoroughly about the role of silver in this perovskite, whether the silver is inside the perovskite structure or on the surface, or what happens in what kind of oxidation state. So you could get hold of one high resolution TEM with the chemical mapping facility at Kyushu University, where this is like a pretty clean surface we got, and this is the elemental mapping where targeted recognition of MN, AG, and PR was there. What was interesting for us that we could prove that both precious diamium and the silver were on the same plane because we substituted precious diamium with silver. And this paper was well received, in fact, in the scientific community. So now the nanomaterials are also finding very interesting application in the personal respiratory protection equipment. Okay, there are many references. And this is N-safe mask, which I'm also using, in fact, from IIT Bombay, IIT Delhi. Okay, so they commercialized it. And I think it's a very good sort of application of nanomaterials or nanoscience and technology. So this mask is pretty popular. I'm also using it. If you see anything is useful for societal purposes, then you can always compare it with the MDGs, UN Millennium Development Goal. And those who used to not get convinced with me that the nanoscience and nanotechnology is something useful, then I used to show them these slides that there are so many MDDs, okay, which can be sort of influenced by the use of nanoscience and nanotechnology. Okay, so these are so many applications. So you need to convince. It was way back in 2007, the Nature Nanotechnology published that nanofiltration, okay, is a beautiful application of nanoscience and nanotechnology, so is tackling the global poverty. Okay. So I'll more or less stop here, and once again I'll compliment Professor Sonawane for one more reason. If he can concentrate on this slide, that this is an estimate that how much of carbon we are saving through this online platform. Okay, there's a beautiful estimation that almost 3 tons per scientist we can save if we avoid going to the international conferences and use the online platform very effectively. So this is just on the lighter side, but it's a wonderful way to do that. So thanks a lot. And finally, I would say that one of the MVPs is the partnership of the goals. So we should look forward for partnership. Most of the work is from my colleagues, collaborators, students, and a lot of different information sources, which I like quoted very seriously. And those are not my thing. We use it only for the benefits of we all or you all. And this last message that it is possible to carry out a lot of research activities on nano with basic facilities. That's what CNR also said. And exploiting collaborators. Okay. If you ask me, I want to have an HR10 in my lab, probably my answer is no. Because I don't have sufficient sample for that. So it's not necessary. You can have basic lab facilities and you can do a lot of work with collaborations. Because like I need to also develop my expertise in the HR10. That's another issue. Why not to collaborate with somebody who's good at HR10? Here I will stop. Thanks again to Professor Sonawane and thank you all for a very patient period.
Thank you very much, sir, for your energetic lecture. Uh, in spite of your busy schedule, you find time for our to contribute your expert lecture in our AICT sponsored faculty development program. I'm confident and I'm hoping that every participants will be enriched listening you and your very fantastic research, and your research is really contributed to the directly to the society and to the nation. Uh, Sir, can you open your chat box so that some questions are there?
No, trying to do that.
If you could see your chat box, you could find some question.
Okay. First of all, thank you very much for all those compliments. I can take it.
This
So what
question, can battery vehicle replace diesel and petrol vehicle in future?
As of now, I would suggest we can discuss what is the best strategy. Okay, it's very difficult to say the battery vehicle will. Everybody wishes. I wish. Although I work on the diesel emission control, I also wish. But as of now, for if you see the even 2040 projection, okay, it looks very difficult. So there will be always a blend of different technologies. Okay, battery is a future, near future rather. Hydrogen maybe will take some time. Okay, but complete replacement of diesel will be a little too difficult because it has got its own advantages. My suggestion will be let's reduce the amount of diesel. Okay, let's increase the share of hydrogen plus batteries and other options, and also make the diesel clean. Okay, because you have plenty of problem in a very briefly. I will explain you that I want hydrogen, I want battery. Yes, it's possible, but at what cost? We know that probably 50% of the people do not have the basic amenities. Of course, we need to invest the money there. Okay? We need to look into their basic need, okay, and do that. But we cannot completely, we cannot imagine right now and for next 20 years, 20 years, that it will be replaced. Then, what is the potential of India in the field of solar energy? Okay, large solar farms in India and organized industry solar farms. Yes, we have a huge potential. There is something called solar map. If you go to the MNRE website, you will find what is the like potential in which area of country. Number one. Number two, yes, we must agree and appreciate and feel proud that India is one of the most aggressive countries when it comes to the solar energy exploitation. The only problem is, we are just a developing economy. So our per capita energy requirement is pretty small, but our population is massive. Once we are developing, our overall energy demand per capita as overall community will go up. Okay, and very unfortunately, despite the very aggressive growth of solar, it cannot be met by solar. Okay, we need to blend. I think they are very polite and hesitant. They are only appreciative of my talk.
There is one question, if you could see, I have just marked it. What are the toxic effects of the nanoparticle based membranes?
Actually, I dealt with the toxic effect of nanoparticles because nanoparticle based membranes if you are asking about the, especially the membrane, then one thing is these nanoparticles should not get dislodged from it. Okay. Once it is dislodged in the, like in the environment, they have all kinds of problems. If it is in the air, we obviously inhale them. Okay. If it is in the water, we can ingest them. So that's the issue. Can battery, I think this we already taken. One more question I see. Day by day, the number of research publications related to nanotechnology is increasing, but I can really see application of them in real world in a large scale. Is this because of difficulty adopting, and if yes, how can we tackle this? It's a good question. Like publications is it requires a lecture by itself. Okay, some other day. Why we need so many publications? There was a article probably in a very reputed magazine that at some point of time the number of deaths were by COVID were less than the number of publications. Then people started claiming that even the number of infections were less than the number of publications in COVID. I had published in paper. So the whole idea of publication is to share your knowledge with somebody else. Not necessarily every publication will translate into a technology. Okay, for sure. Okay, if you are like, for example, we just floated the idea, we did not even do the research, but it got accepted in a very reputed journal. That why not to explore that instead of glass surface, interaction of particles with those things on the glass surface. Similarly, yes, I understand that majority of the publications have nothing to do with the application, but you cannot say that there are no applications. There are many, many applications of nanotechnology based membranes, energy applications. Yes, if you calculate the translating of 2000 into one technology, that always happens because we have to evolve in science. We need to also have an objective of capacity development or HR development. So half of the publications come from that. There's nothing wrong. The only thing is we should be very, very ethical and honest about publishing the data. Even if it is 10 or 20 publications not running technology, absolutely nothing wrong. I don't think so.
So, Dr. Sir, most of the participants have said that this is very excellent session.
I'm very thankful to them, very kind of them for this appreciations.
Is it a question? Is inhalation of nanoparticle a concern? What is inhalation of nanoparticles concern?
And that we already covered. Like for example, if you are working in a factory where the nanoparticles are produced, or if you are using nanoparticles in a device and those get released in the air, they are quite similar to diesel exhaust particles. So naturally, any particles, any foreign particles made into your lung will have its own health implication. So yes, we have to be careful, but we never use nanoparticles like that. The only thing is whenever you are dealing with the nanoparticles, say manufacturing or anything, okay, so you have to be careful. That can be taken care. Fine. So thank you very much.
Dr. Labhsetwar sir, thank you very much for sharing your knowledge at this platform.
My pleasure.
Thank you. Bye
Bye bye. I'll take leave.
bye.